Hi all, in this class our topic is differential entropy, and this is the first topic coming from third module, and mainly the third module deals with different continuous sources and channels. And now we can see what is differential entropy. So in previous videos we studied the marginal entropy for a discrete random variable x, and is defined as h of x equal to summation of I equal to 1 to n p of xi log of 1 by p of xi to the base 2. And now we can define the entropy for a continuous random variable x with the probability density function is given as fx of x. And so using this probability density function we can define the differential entropy similar to the marginal entropy defined for discrete random variable. So it is defined as h of x equal to small h capital X, h of x equal to integral minus infinity to infinity fx of x log 1 by fx of x to the base 2 dx. So we can see that here the notation is changed, and instead of summation for continuous random variable we are using the integration function, and here we are using the probability density function. So according to this differential entropy, h of x is equal to summation of, instead of summation, integration of minus infinity to plus infinity fx of x log 1 by fx of x to the base 2 dx. So that's our differential entropy. So now we can see how we derive this expression. For that we are taking our continuous random variable x as the limiting form of a discrete random variable, and we assign that xk is equal to k into del x. So next our aim is to derive this differential entropy expression. For that we are taking our continuous random variable x as the limiting case of a discrete random variable in such a way that one symbol xk is equal to k into del x. K may be 0 plus or minus 1 plus or minus 2 etc., and del x nearly tends to 0. So by definition the continuous random variable x assumes a value in the interval xk to xk plus del x with probability density function is defined as fx of xk del x. So this is our probability density function for this continuous random variable within the limit xk to xk plus del x. So permitting del x to tends to 0, the ordinary entropy of the continuous random variable x takes the limiting form as h of x equal to limit del x tends to 0 summation of k equal to minus infinity to plus infinity fx of xk del x log of 1 by fx of xk del x to the base 2. So we are considering our continuous random variable x as the limiting form of discrete random variable, and we assume the values as xk is equal to xk del x, and we assign that this continuous random variable ranges from xk comma xk plus del x, and this with the probability fx of xk del x. So we can limit this as the limiting case, we can take this as limiting case of discrete random variable, and for a discrete random variable we know that h of x equal to summation of I equal to 1 to n f of p of xi log of 1 by p of xi to the base 2. So we are taking that as here this continuous random variable as the limiting case of this discrete random variable. So we can write this h of x as limit del s tends to 0 summation of k equal to minus infinity to plus infinity fx of xk del x log of 1 by fx of xk del x to the base 2. Then we can rewrite this log 1 by fx of xk del x to the form as limit del x tends to 0 summation of k equal to minus infinity to plus infinity fx of xk del x log of 1 by fx of xk to the base 2 minus another term is summation of k equal to minus infinity to plus infinity fx of xk del x log of del x to the base 2. So we are rewriting that log term. So then you will get it as rewriting the order of terms, we will get it as limit del x tends to 0 summation of k equal to minus infinity to plus infinity fx of xk log of 1 by fx of xk to the base 2 into del x minus, we are taking this log to del x outside, remaining is summation of k equal to minus infinity to plus infinity fx of xk into del x. So we can write this fx of xk, thus fx of xk as fx of x itself, and this as del x tends to 0, the summation becomes summation equation becomes integral equation. So we can write it as integral of minus infinity to plus infinity fx of x log of 1 by fx of x to the base 2 del x become dx minus, second case is limit del x tends to 0. We are taking this limit del x tends to 0 instead. So you will get limit del x tends to 0. Remaining is log of del x to the base 2. Summation is changed as integration of minus infinity to plus infinity fx of x dx. And we know that the probability density, if you are integrating the probability density function between two interval, you will get it as 1. That means minus infinity to plus infinity fx of x dx is 1. So that term become 1. So you will get it as the first term is represented as h of x minus limit del s tends to 0 log to del x. So that is the our h of x changed as h of x minus limit del x tends to 0 log del x to the base 2. So we can see that the second term, the limit as the limit del x approaches 0, the term minus log to del x approaches infinity. We know that this minus log del x is log 1 by del x as del x tends to 0, 1 by 0, that become infinity. So this means that the entropy of a continuous random variable is infinitely large. So we can say that the continuous random variable is infinitely large. So we also expect that for a continuous random variable we can assign any value between the interval minus infinity to plus infinity. So to encounter this uncountable infinite number of probable outcomes, and to avoid that problems, we are taking this log to del x term in this log to del x term as a reference term. So this h of x we are taking as the differential entropy. That means the right hand side h of x, we are taking the differential entropy with the term minus log to del x. We are taking that as reference. So we can say that the information transmitted over a channel is actually the difference between two entropy terms that have a common reference. The information will be same as the difference between the corresponding differential entropy terms. So this h of x is called the differential entropy of the continuous random variable x, and this minus log to del x we are taking the reference. So actually the information will be same as the difference between the corresponding differential entropy terms. So we can write this h of x as minus infinity to plus infinity fx of x log of 1 by fx of x dx. That is our differential entropy. Minus integral of minus infinity to plus infinity fx of x log of 1 by fx of x to the base 2 dx. So this fx of x is called the probability density function. We can also define the joint differential entropy as well as conditional differential entropy. The joint differential entropy is defined as h of xy equal to double integral of fxy of x comma y log of 1 by fxy of x comma y dx dy, where this fx comma y of x comma y is called the joint density function. And similarly the conditional differential entropy h of x by y is equal to double integral f of x comma y of x comma y log of 1 by fx of x by y. And this first probability, that is fx comma y of x comma y, represent the joint density function, and this fx of x by y represent the conditional density function. So this equation is called as joint differential entropy as well as conditional differential entropy.